welcome to the Explainer. So today we're tackling a seriously messy problem, electrical wiring. And we're going to solve it by learning the sleek, universal language of standard circuit diagrams. Let's just dive right in, because by the end of our time together, you're going to be reading and designing electrical circuits like an absolute pro. Take a look at these two approaches. On the left, we've got this super tangled, realistic drawing of a battery and a bulb. Honestly, it takes way too much time to draw, it's incredibly messy, and it's basically impossible to replicate perfectly every time. Just imagine being an electrical engineer and having to sketch out a highly detailed, realistic battery every single time you had a new idea. It would literally take forever. But then look over on the right. It's a clean, straight-line diagram of that exact same setup. Now ask yourself, which one would you rather draw 100 times? Yeah, exactly. Because here's the thing. Real electrical setups, like the metallic copper tracks you see on this printed circuit board, are incredibly complex. I mean, how could anyone possibly troubleshoot such a chaotic web without getting totally lost? Trying to trace just one single path with your eyes is an absolute headache. And that is exactly why scientists and engineers desperately needed a better, universally understood way to communicate their designs without all the visual clutter. And that elegant solution is the circuit diagram. You can kind of think of a circuit diagram as a universal map. It's a map that absolutely any scientist, in literally any country, can easily draw and interpret right away. It completely strips away all that physical clutter we just talked about, and it focuses purely on how the electricity flows. It represents every piece of the puzzle simply, leaving absolutely no room for confusion. Think of these standard symbols as the alphabet of a secret global language. Let's quickly run through the foundational letters you're going to need to know. We've got the ammeter, which expertly measures the current, the energy-providing cell, which powers the whole shebang, the lamp, our visual indicator that gives out light, the switch, which easily stops or starts the flow of electricity, and finally, the buzzer for making an audible sound. Pretty straightforward, right? And honestly, this brilliantly illustrates the real power of this system, its absolute universality. Even though electrical components, like all these wildly varied types of lamps you'd find in the real world, look completely different from one another, they all share the exact same simple circle and cross symbol on paper. The core insight to remember here is that function is what matters, not physical appearance. But just like any spoken language, there are strict grammatical rules for writing it down. First off, wires must always be drawn with perfectly straight lines, no squiggles allowed. Second, there must be zero gaps in those lines, especially at the corners, simply because electricity cannot flow across an empty space. Third, wires are never ever drawn straight through the middle of a component. Doing that implies a short circuit and makes the diagram totally impossible to read. And crucially, for a cell symbol, the longer line is always the positive terminal. Okay, so now that we know our alphabet and our grammar rules, let's go ahead and read our first functional sentence together. This simple arrangement of a cell, an open switch, and a buzzer perfectly describes the job of your standard front doorbell. When the switch is pushed closed by someone outside a door, it smoothly completes the path, making the buzzer sound to get your attention inside. Makes perfect sense, right? Let's see how this builds into something a bit new by reading a slightly more complex circuit. Now, this one features a cell and a switch, just like before. But notice it substitutes the buzzer for a lamp to provide light. Plus, it introduces an ammeter into the mix to actually measure the electric current flowing through the system. So, the really crucial point here is understanding why we would even bother adding that ammeter. Well, in this specific setup, the ammeter does a vital job. It monitors the current, basically acting as an early warning system. It tells you if the cell is running low on stored energy. If you didn't measure this, the lamp would just slowly dim until it abruptly dies, literally leaving you sitting in the dark without any warning. Now, I want to test your brand new language skills with a quick little challenge. A student named Arun tried drawing a simple circuit with a cell, a switch, and a lamp, but he made 3 critical errors in his grammar. I'm going to give you a few seconds. Do you think you can spot them? Let's examine Arun's flawed diagram together. First, I want you to start by checking out the top left corner near the switch. Next, move your eyes over to how the wire interacts with the lamp component on the right side. And finally, look very, very carefully at the symbol he used for the cell itself over on the left. Have you found all 3? Okay, let's see how you did. First, there is a totally disconnected gap in the wire at the top corner, and as we learned earlier, electricity is definitely not going to flow through a gap. Second, the wire is drawn slicing right straight through the middle of the lamp symbol. This creates a ton of visual confusion and incorrectly implies a short circuit. And third, the cell symbol is drawn incorrectly with touching lines, which totally blurs the positive and negative terminals. If you caught all those, huge congratulations! You are officially reading circuits like a scientist. Now that you can fluently read standard diagrams and easily spot mistakes like a pro, it is time to step up and start writing your own electrical paragraphs. You can use these standard symbols to design your very own circuits to accomplish specific, complex, real-world jobs. You literally hold the blueprinting power. For example, what if you were asked to design the electrical system for a car's headlights? Well, you take what we've learned and start combining your symbols. First, you'd need to provide a robust power supply, like a cell. Second, you'd add a master control switch. And finally, you would connect two lamps arranged side by side so they will both switch on simultaneously the second the driver hits the lights. Really, the possibilities are endless here. You could even map out a whole home security system. Think about a buzzer on a front door paired with a lamp that flashes at the exact same time, giving you a visual and an audible alert. You can design and verify all of this using just your standard symbols without ever having to draw a single messy, realistic wire. It's a total game changer. As we wrap up this explainer, I'm going to leave you with a final, slightly provocative puzzle to ponder. As you become more and more fluent in this universal language, is it possible for two completely differently drawn diagrams to both be perfectly correct for the exact same job? Think about how the path of electricity actually works. Keep questioning, keep drawing, and I'll catch you next time.